Next up is the force on a closed loop. Here's my loop of wire. And I'm actually going to show that it's actually got some width to it. And I'm going to make the current go this way. I is this way, which of course means that I is this way, I is this way, and I is this way. And I'm going to just make the magnetic field so you see that it is extending. This whole thing is in a magnetic field. Let's first figure out what's the direction of force on this leftmost part of our loop. I've left out the battery for simplicity. There's got to be a battery unless it's a superconductor. Could be a superconductor. Just get it going. You don't need any battery. Go ahead and figure out the direction of force on this section right here. What is the direction of force on that section right there? Go ahead and use your right-hand rule. So IL cross B, the direction of current is the direction of the motion of those supposed positive charges. So you put it's the currents going down, fingers in direction of velocity, which is the same as direction of current of positive charges. Then you got to bend it in the direction of the magnetic field, which is this way to your right. The force on this side is out of the page. Let's figure out the force on that section, the bottom part right there. Go ahead and use your right-hand rule. You're going to have a weird issue with this. Yeah, now I suppose you could probably twist your hand in a way to make this work, but notice that the current is parallel to the magnetic field. What is the sign of theta? Well, what's the angle between the current and the magnetic field here? Notice that theta is equal to 0 for this part. Theta equals 0. So what is the sign of 0? 0. The cross product gives us no force over here. What other part of this loop can we easily do now? Anti-parallel, force is 0. Whenever the magnetic field is parallel to a moving charge, velocity, or a current, the force is 0. Now let's do this last one. Go ahead and figure out the direction of force for that last piece right there. What's the force on this side? You can pretty much easily figure it out using your right-hand rule, or just saying, oh, well, if it's down and it's out of the page, over here, the force on this side will be which way? Into the page like that. Notice two things. First of all, what will the net force on our loop be? The net force is 0. Is there a torque, however? Yes. There is going to be a torque about, I'm going to use, let's go to the black color here. About this axis, there will be a torque. There is a torque on a loop in a magnetic field. Guess what we just invented? A motor. That is how all electric motors work. There's a torque on a loop. Now, there's a couple of tricks you have to be aware of. You got to switch the direction of current so it doesn't just flip and stop. But that can easily be done. Or you can do like Tesla did and use alternating current, which we don't have to cover in this course. Okay, so notice that, and here's where we left off here. The net force on a loop is 0. However, there is, this is in a uniform field, by the way, there is a torque on this loop. So although the net force is 0, there's a torque on the loop. The torque on a loop in a magnetic field. It's not too hard to figure out. What I've got here is I've got a loop that's got height A that away. It has got width little b right there. Okay. And it's got a current. In this situation, the current's going around counterclockwise. I've got a magnetic field going to the right. Now we can figure out the individual forces, but there's a much easier way to do it. Here's the side view of what we're looking at. Our magnetic field is to the right. We're looking at this. There's the point right in the middle here. So where we're looking at this is from the side where the B is toward us. In other words, we're looking at this from, if our eye was over here. Here's our eye right there, looking that away up at this thing. and that's where our I is. So this is what it looks like from this angle. So notice that what I've got is current coming toward us right here. Current is toward us. That's what that dot is. That's the current toward us. So the force, using our right-hand rule, if the current's coming toward us, point your right hand towards you, and your fingers got to bend in the direction of the magnetic field, so the force is up. Does everyone get a force up that way? That is F sub B. Again, I believe your equation sheet for your C, they may use F sub M. They've changed that in recent years. Yeah, so they use F sub M. But on this side, the force is down. Now, because they're equal forces, it's going to rotate about its center right there. So I can figure out what the torque is. And let's go ahead and we get to review torque. Awesomeness. So let's figure this out. Now, I get the maximum torque when I is perpendicular to B. Okay? Our maximum torque is R cross F, where R is the, do we remember the rhyme? Time to start reviewing. R is the displacement from axis of rotation to point of force application. Notice that that is just half of B. Check this out. Here's our axis of rotation right there. That's the axis of rotation. The displacement from there to there is only half of B. That's where we get that B over 2. So my torque is B over 2, that's R, times the magnetic force right there. And then I've got to add to that the torque caused by the other side, which notice the torque's going to be in the same direction. Why? Because both of these forces are causing a which directional torque? How would you describe the direction of torque? There's a couple ways of doing it. Clockwise torque, or using your right-hand rule, folks, we can represent that torque with one vector. Spin your fingers around in the direction that this thing will spin. It'll spin clockwise, so move your fingers clockwise. What vector direction could you represent clockwise with? A vector into the page. Okay, so that will give us this, B times FB, and then what I'm going to do is that is B times the, notice that, now where am I getting this? How do I get the magnetic force being IAB? Why is that? Hint, what is the force on a wire carrying current? Let's go back to the general equation for that. IL cross B. So what is that A in this case? A is the length of our wire. Notice that the magnetic field is acting on this whole length right there. Why do I not have to worry about the length of wire B when I'm figuring out the force? It's parallel. There's no force on the part with length B. There's only a force on this. So ILB, IL cross B just gives us, when they're perpendicular, IAB. And I've rearranged it to make it look like this. I times B times the A times B, which is the area. Our maximum torque that we get is the current in the loop times the area of the loop.
Times the B field.
We are going to define the vector A. Again, it's normal to the plane of the current loop, but it has a specific direction. Before, with just a flat plane, you could pick either direction for the A vector. For this, you must use the right-hand rule. So what you do is you take your fingers in the direction of the current. Everyone, look at this current loop right here and tell me, well, curl your fingers in direction of current. Which way is the A vector, the area of this loop? It is out of the page towards you. That is the direction our A vector must point. So our summary statement here is this. If we do that, then I'm just going to jump over to here. You get torque is IAB sine theta, or very simply put, the torque on a loop is IA crossed on the B field, where A is the area vector and the A vector points in the direction determined by the right-hand rule. You just curl your fingers in direction of current. Your thumb points in the direction of the A vector. IA cross B is the torque on a current loop. Very useful for motors.